Welcome to Late Night History. Somewhere on the far side of the planet right now, there is a wave that is supposed to arrive and never will. It set out from an earthquake hours ago, or perhaps it was years ago, and it traveled down into the body of the Earth, down through rock that no eye has ever seen, and at a certain depth it met something it could not cross. And so it stopped. It simply ended. And on the other side of the world, a delicate needle traced its quiet line across a turning drum, waiting for a signal that, by every expectation, should have come. And the signal did not come. There was only silence. A small, patient, perfect silence. Hold that image for a moment before we go anywhere at all, because tonight, that missing wave is the whole story. That absence, that thing that should have arrived and didn't, is how we came to know the inside of our own planet, not by going there, not by sending a probe or a person or a single instrument into the deep. We learned the shape of the world's hidden interior by listening very carefully to where the planet goes quiet. So settle in, let your shoulders fall a little heavier into wherever you are lying. There is nowhere you need to be and nothing you need to follow closely. If your mind drifts off somewhere in the middle of all this, that is exactly as it should be. You can let the words wash over you like water moving slowly through stone in the dark. Tonight we are going to do something strange and gentle together. We are going to map a place that no human being can ever reach. A sealed room, you might call it. A room at the center of everything, with no door, no window, no way in and no way out. And yet we have drawn its walls, measured its heat, and weighed what fills it. And we did all of it from the outside, listening. Before we begin the descent, I'd love to know where in the world you are listening from tonight. Some of you are in deep winter, with the cold pressing against the glass, and some of you in the thick, warm hush of summer. If you feel like sharing the name of your town or your country in the comments, leave it there for me, and I'll read it. It's a quiet pleasure of mine picturing all the different darknesses these stories travel into. And if you've found your way here for the first time and you think you might like to fall asleep to more slow journeys like this one, you can subscribe and there will always be another waiting. But none of that is urgent. The only thing that matters tonight is rest. Let me carry the thinking. You just breathe now. Let us begin with how little we have actually touched. You might imagine, given how clever we have become as a species, given the rockets and the deep-sea machines and the instruments that can weigh a single atom, that somewhere along the way we surely dug down and had a proper look at the inside of the Earth. It feels like the sort of thing we would have done. And we did try. We tried as hard as we have ever tried to do anything. In a cold and windswept corner of the far north of Russia, on the Kola Peninsula, near the border with Norway, a team of Soviet scientists and engineers set out, beginning in the early 1970s, to drill the deepest hole that human beings had ever made. They were not looking for oil. They were not looking for anything they could sell. They were doing something purer and stranger than that. They simply wanted to go down. They wanted to drill straight into the crust of the Earth as far as machinery could possibly take them and see what was there. They called it the Kola Super Deep Borehole. And year after year they ground their way downward, and the hole crept deeper and deeper into the bedrock. It is hard to picture this, so let me give you something to hold on to. Imagine a drill but not a single solid rod, because no rod could be that long. Imagine instead an enormous string of pipe, kilometers of it, hanging straight down into the earth, with the drill bit turning at the very bottom of all that weight. To deepen the hole, they had to spin the entire column. And the deeper they went, the more impossible it became, because the bottom of that column was now somewhere no one had ever been. By 1989, after nearly 2 decades of patient, grinding work, they reached the deepest point. The bottom of the Kola super-deep borehole sat 12,262 meters below the surface, just over 12 kilometers straight down. It remains, to this day, the deepest hole that human beings have ever drilled into our own planet. 12 kilometers. Say it slowly to yourself. It sounds like a great distance, and in human terms, it is. If you laid that hole on its side, it would run the length of a city, end to end and then some. If you fell down it, you would fall for the better part of a minute before you reached the bottom. By every measure of a human being and a human life, 12 kilometers is deep and dark and far. And now here is the thing that ought to humble all of us gently before we go any further. The distance from the surface of the Earth down to its very center is not 12 kilometers. It is about 6,371 kilometers. That is the radius of our planet from where you are lying right now down to the point at the absolute middle of everything. 6,371 kilometers of rock and metal beneath you. So let us put those two numbers side by side, the way you might lay two objects on a table to compare them. The deepest we have ever reached, 12 kilometers. The distance to the center, 6,371. Do the arithmetic slowly, and a remarkable, almost embarrassing little figure falls out of it. The deepest hole we have ever dug reaches about 19/100% of the way to the center of the Earth. Not 19%, not even 2%, 0.19%, barely 0.2% of a single percent. Let me find you a way to feel that, because the number alone is too thin to carry the weight of it. Imagine the entire Earth shrunk down to the size of an apple, sitting in the palm of your hand. The whole vast planet, every ocean, every mountain, every kilometer of fire and stone compressed into a single apple. Now ask yourself how deep on that apple our deepest drilling would go. The answer is that it would not even break the skin. It would barely scratch the waxy surface of the peel. Everything human beings have ever directly seen of the inside of the Earth, every rock we have ever held that came from below, every borehole and every mine shaft, all of it lives within that paper-thin outer skin of the apple. Beneath it, the entire glistening flesh of the fruit, the whole interior of our world, lies untouched and unseen. And here is the part that turns this from a humbling fact into something close to a mystery. The people at Kola did not stop because they had reached some natural finish line. They did not run out of money in any simple sense, and they did not strike some impenetrable wall of unbreakable rock. They stopped because of something far stranger, something the deep itself did to them. You would think, wouldn't you, that the danger of digging deep is that the rock gets harder and harder until at last it is too solid to break. That is what our everyday lives teach us. The deeper you go, the more solid, the more stubborn, the more unyielding things become. But that is not what happened at the bottom of the Kola hole. The opposite happened. As they drilled deeper, the rock grew hotter than anyone had planned for. Their predictions, based on what was known at the time, suggested that at that depth they would meet temperatures of around 100 degrees Celsius, hot enough to boil water, certainly, but manageable. Instead, when they reached the bottom, the rock around them was roughly 180 degrees Celsius, far hotter than expected, hot enough that the ordinary, sensible rules of solid rock began to dissolve. Because rock, when it gets hot enough and is squeezed hard enough, stops behaving like the brittle stone we know on the surface, the stone that cracks and chips and shatters. It begins instead to behave a little like something soft, a little like warm wax, or like very stiff clay, or like honey on a cold morning that flows, but flows so slowly you can hardly believe it is moving at all. At the bottom of the Kola super-deep borehole, the rock was no longer a hard wall to be conquered. It had become something that flowed, and a hole drilled into rock that flows does not stay open. It closes, It oozes shut behind you, slowly, patiently, like a wound healing, like the surface of a pond closing over a dropped stone. The deeper they pushed, the more the earth quietly pressed the hole closed again, sealing itself, refusing to be opened. Sit with that for a moment, because it is one of the most quietly astonishing facts in this whole story. The deepest hole that human beings have ever made was not defeated by hardness. It was defeated by heat and by the strange way that hot, deep rock begins to flow instead of break. The earth did not slam a door in our faces. It simply, gently, softened around our drill until our drill could go no further, and then it closed the small wound we had made and went back to being whole. So that, then, is where we stand at the very beginning of tonight's journey. We have never been deeper than that paper-thin scratch on the apple's skin. We can never go to the center. No probe we have ever built could survive the heat and the pressure. No human eye has ever looked upon anything below about 12 kilometers, and in all likelihood, no human eye ever will. The interior of our own planet, the place we are all riding upon as the Earth turns through the night, is, in the most literal and unyielding sense, unreachable. And yet we have a map. We know there are layers down there, and we know roughly how thick each one is. We know that somewhere far below there is a place where solid rock gives way to molten metal. We know that deeper still, at the very heart, there is a solid ball of iron, hotter than you can easily imagine, and we even know roughly how big it is. We know the heat down there and the crushing pressure in numbers we can write down. We have drawn the walls of a room no one can ever enter. So the real mystery of tonight, the one we will turn over slowly together as you drift towards sleep, is not what is down there. We will get to what is down there in time. The deeper and stranger mystery is this: how could anyone possibly know if no one has ever been within 99.8% of the way to the center, if every deep probe would be crushed and cooked long before it arrived, if the rock itself flows shut around our deepest hole, then how on earth did we draw the map at all? The answer is so elegant, so quiet, so unlike brute force, that once you understand it, you may find you love it. We did not break our way in. We listened. Here is the heart of it. Now and then, somewhere on the surface of the planet, the ground shudders. An earthquake, two great masses of rock that have been pressing against each other for years suddenly slip, and in that instant they release an enormous shiver of energy. We mostly think of earthquakes as something that happens to the surface, something that shakes buildings and cracks roads, and of course they do. But that is only the part we feel. The energy released by an earthquake does not only travel along the surface, it travels down. It plunges straight into the body of the planet, spreading out in all directions, racing through the deep rock as a kind of trembling, a wave moving through the stone the way sound moves through air, or the way a ripple moves through water. And these waves, these tremors, moving through the deep earth, do something miraculous. They pass all the way through the interior, through the layers and the molten metal and everything else hidden down there. And then they come back out the other side, and they reach the surface again, sometimes on the far side of the world. And when they arrive, they brush against the most patient instruments human beings have ever made: seismographs. Quiet machines often kept in still, dark places, designed to feel the faintest trembling of the ground and to record it as a line drawn on a turning drum, or, in our age, as a wavering trace on a screen. So here is the great realization, the one that everything else tonight grows out of. Earthquakes are the only messengers we have. They are the only things in all the world that routinely travel down through the deep interior of the planet, all the way through the unreachable places, and then return to the surface carrying news. No human can go down there, no instrument can survive down there, but these waves go down there every single day, again and again, and they come back. And like a traveler returning from a country no one else can visit, each wave carries the marks of everything it passed through along the way. If we are clever enough and patient enough to read those marks, then the wave will tell us about the unreachable rooms it traveled through. The wave becomes our eyes. The wave becomes our hands. The wave goes where we cannot, and it comes home and whispers what it found. Now, to read that whisper, we have to understand a little about the waves themselves, and I promise to take this gently because it is the one small piece of machinery you need for the whole rest of the story, and once you have it, everything else will open up on its own. When an earthquake sends its energy down into the planet, it does not send only one kind of wave. It sends two main kinds, two different ways of trembling through the rock. And the difference between them turns out to be the single most important thing in this entire night. The first kind we call the P wave. Now the names here are wonderfully plain and human, and they will help you remember everything. So let me tell you where they come from. When the trembling from a distant earthquake reaches a seismograph, the two kinds of wave do not arrive together. One of them is faster, and so it arrives first. The other is slower, and so it arrives second. And the scientists who first studied these traces watching the needle named them in the simplest possible way by the order in which they showed up. The first one to arrive, the fast one, they called the primary wave, the P wave, P for primary, for the one that comes first, and the second one to arrive, the slower one, they called the secondary wave, the S wave, S for secondary, for the one that always comes second, trailing patiently behind its faster sibling. So already you have a feeling for them. The P wave is the swift one, the one that races ahead and reaches the far machine first. The S wave is the slower one, the one that always comes a little later in the wake of the other. And if you ever see the trace of a great earthquake, you will see exactly this. First, after a long quiet, the needle jumps as the P wave arrives. Then, a measured stretch of time later, it jumps again, more violently often, as the slower S wave finally catches up. The very gap between those two arrivals, that pause between the first jump and the second, turns out to tell us how far away the earthquake was. But that is a detail for another time. For now, just hold the two characters in your mind. The fast first one, primary, P, the slow second one, secondary, S. But the speed is not really what matters most about them. What matters most is how they move. And here the two waves are profoundly, almost philosophically different, and this difference is the secret door through which we will eventually walk into the center of the Earth. The P wave, the fast primary one, moves by pushing and pulling. Picture this. Imagine a long spring, the kind of coiled toy that walks downstairs, stretched out across a floor. If you take one end and push it sharply toward the other end, and then pull it back, you will see a little zone of bunched up coils travel along the spring, a compression that races from one end to the other. Push and pull, squeeze and release. That is exactly how a P wave travels through rock. It compresses the material in front of it, then lets it spring back, then compresses the next bit. And so the wave of squeezing travels onward, push-pull, through the stone. It is, in a real sense, a wave of pressure. And here is the wonderful thing about a wave of simple squeezing. Because you can squeeze almost anything. You can squeeze solid rock, of course, but you can also squeeze liquid the way water carries the pressure wave of a stone dropped into a pond. And you can squeeze gas, which is how sound, a pressure wave, travels through the air. So the P wave, the push-pull wave, can travel through solids, through liquids, and through gases alike. There is nothing it cannot pass through because everything in the world can be squeezed, at least a little. The S wave is a different creature entirely. The S wave does not push and pull along its direction of travel. Instead, It shakes side to side across its direction of travel. Picture now a long rope tied to a post at the far end and you holding the near end. If you flick your wrist up and down, you send a hump traveling along the rope, a wave that moves forward while the rope itself only moves up and down, sideways to the direction the wave is going. That sideways shaking, that shearing motion, is how an S-wave travels. The rock is not being squeezed forward and back, it is being shoved sideways, sheared, like a deck of cards slid across itself, one layer sliding past the next. And because of this, scientists give the S-wave another name as well. They call it a shear wave because it works by shearing, by that sideways sliding motion. And now we arrive at the single most important fact in this whole night, the one quiet fact upon which our entire map of the unreachable interior is built. So let me say it slowly and then say it again a different way, so that even half asleep it has a chance to settle into you. A shear wave, an S-wave, cannot travel through a liquid. It simply cannot. It is impossible. Why? Why can the push-pull P wave sail right through water and molten metal while the sideways shaking S-wave is stopped dead? The answer lies in what it really means to be a liquid. Think about what happens when you try to shear a solid. Take a block of solid rubber or a brick or a piece of wood and try to slide the top of it sideways relative to the bottom. The material resists you, it holds itself together. The top is bound to the bottom, and if you shove the top sideways, that sideways push gets passed down through the whole material because the material has what we call shear strength. It can resist being sheared. It can carry a sideways shove from one part of itself to the next. Now think about trying to shear a liquid. Take a glass of water and try to push the top layer of the water sideways. What happens? Nothing holds. The top of the water just slides freely over the water below it. There is no resistance to the sideways motion, no binding, no holding together against a shear. A liquid has no shear strength at all. The molecules slip past one another without complaint, and because a liquid cannot resist a sideways shove, it cannot pass one along. There is nothing to carry the shearing motion forward, so when a shear wave, an S-wave traveling through solid rock, arrives at a layer of liquid, there is suddenly nothing there that can carry it. The sideways shaking has nothing to push against, and the wave dies. It stops at the doorway of the liquid and goes no further. It simply ends. Do you feel now the shape of where this is going? Do you feel the first faint outline of that sealed room beginning to appear in the dark? Because here is the promise of it, the promise I am going to leave hanging over us as you drift, so that we can return to it later and close the loop. If, somewhere deep inside the earth, there were a layer of liquid, then a wave traveling down into the planet would behave in two very different ways depending on which kind of wave it was. The push-pull P wave, able to pass through liquid, would carry on down through that liquid layer, bending perhaps, slowing perhaps, but surviving and coming out the other side. But the sideways shaking S wave, the shear wave, arriving at that same liquid layer, would be stopped, killed, unable to cross. And on the far side of the planet, in the great death zone beyond that liquid, the seismographs would wait and wait for an S-wave that, by the simple, unyielding rules of physics, can never arrive. That is the missing wave I spoke of at the very beginning of tonight, the shear wave that should reach the far side of the world and simply doesn't. The silence on the turning drum, the needle that waits and traces nothing. We are going to find, as we go deeper into this story, that there really is such a silence, there really is a ring around the Earth where the S-waves never come. And the only thing in all of physics that can explain that silence is a layer of liquid deep down that no shear wave can ever cross. But I am getting ahead of us, and that is all right, because tonight there is no hurry at all. We have a long, slow descent ahead, and we will take it one gentle layer at a time. We have established the strange, humbling foundation of everything, that we cannot go down there, that we have scratched barely 0.2% of the way to the center, and that even there the rock grew so hot it flowed shut around us, that the only messengers we have are the trembling waves of distant earthquakes passing through the deep and returning to the surface to brush against our patient machines, and that those waves come in two kinds, the fast push-pull P wave that can cross anything, and the slower sideways S wave, the shear wave, that is stopped cold by liquid because liquid has no strength to resist a sideways shove. Everything else we map tonight, every boundary, every hidden sphere, every number for the heat and the crushing pressure, all of it is built upon those few simple ideas. A few kinds of wave, a few patient machines, a handful of curious people watching needles trace lines on paper and asking again and again the most patient question in all of science. The wave should have arrived by now. Why hasn't it? And what does its absence tell us about the rooms it tried to cross? So let your breathing slow. Let the weight of your body settle further into the dark. Picture, if you like, one of those quiet seismographs, somewhere in a still building far from any city, its needle resting, waiting, ready to feel the faintest tremor arrive from half a world away. Picture the long patience of it, the way it would wait through the silence of an ordinary night for a signal that might come or might never come. That patience, that listening in the dark for a wave that may or may not arrive, is the truest spirit of this whole story. We mapped the unreachable not by force, but by waiting and by paying very close attention to silence. And the first thing those patient listeners ever found, the very first hidden boundary anyone ever detected inside the Earth, came not from a missing wave at all, but from a wave that arrived too soon. A wave that on a quiet morning more than 100 years ago showed up at a distant station earlier than anyone expected, as though it had found a faster road somewhere down below. A road none of us had ever known was there. It was October 1909, and a moderate earthquake had shaken the ground somewhere beneath the Kola Peninsula. By the standards of great seismic events, it was not remarkable. The shaking was felt across a broad region, buildings trembled, people steadied themselves against doorframes and then went on with their days, and the event would likely have faded without particular scientific consequence, as so many similar events had faded before it. Except for one thing. A Croatian meteorologist named Andrija Mohorovičić was sitting with the seismograph records. Mohorovičić worked in Zagreb, and he had, by 1909, spent years in the patient company of seismographic instruments, reading their output, making sense of the slow and fast arrivals of waves from distant sources. He was not a man given to dramatic pronouncements. The records he kept and the methods he applied were careful and methodical, which is perhaps why what he noticed that October was so significant. He noticed, looking at the records from various stations spread across different distances from the earthquake, that there were two distinct arrivals of the same type of wave reaching the same stations, and that the faster of those two arrivals was arriving considerably earlier than a wave traveling through ordinary crustal rock should have. This requires a moment to sit with, because it is the kind of observation that, once you understand what it means, changes the way you read the ground beneath your feet. When a wave travels through rock, its speed depends on the properties of that rock. Denser, more rigid rock carries a wave faster, just as a tighter drumhead vibrates a sound faster than a loose one. Softer, less dense rock slows a wave down. Mohorovičić had been trained on the reasonable assumption, shared by everyone in his field at the time, that the waves from a nearby earthquake would travel through the crust along more or less direct paths, following the shortest route, and would arrive at distant stations at speeds consistent with the known properties of crustal rock. But some of these waves were not behaving that way. They were arriving too quickly, and not just a little too quickly, but significantly early, in a way that simple variation in the crust could not explain. Mohorovičić sat with this. He thought about it carefully. And then he arrived at the only explanation that fit the numbers he was looking at. There had to be a layer beneath the crust, he reasoned, with different properties. A denser, faster layer. And some of the waves were diving down into that layer, speeding up as they entered it, and then bending back upward to the surface, traveling a longer path in terms of pure geometry, but arriving sooner because they had spent part of their journey inside something much faster than ordinary crustal rock. Think of it like this. Imagine you want to cross a large field and you have two options. You can walk straight across the grass, which is slow going, or you can take a slightly longer route that gets you onto a paved road for most of the journey, where you can move much faster. If the road is fast enough, the longer route is actually quicker. That is what those seismic waves had done. They had found the road. And the road had a name, though no one had known it existed until Mohorovičić found the evidence for it in those 1909 records. The boundary between the crust and what lies below, the surface where waves suddenly speed up as they dive from one kind of rock into another, became known as the Mohorovičić discontinuity. The name is a formidable one, and scientists working with it every day are generally grateful that it also goes by its shorthand, the Moho. But the full name carries its own dignity, and it belongs entirely to that quiet Croatian scientist who noticed, in the aftermath of an unremarkable Balkan earthquake, that the planet had a hidden flaw below its familiar surface. The Moho, at its simplest, is the base of the crust. Everything above it is the crust, the relatively thin outer shell we live on, the rock of continents and ocean floors, the familiar geology of mountains and valleys and sea floors spreading. Everything below it is the mantle, something chemically and physically distinct, denser, hotter, carrying waves faster and extending downward for a great distance beneath our feet. The exact depth of the Moho varies considerably depending on where you are standing. Under the oceans, where the crust is geologically young and relatively thin, the Moho sits at only about 5 to 10 kilometers depth. You could, in theory, drill to it from the ocean floor with rather less effort than from dry land, which is precisely why later engineers trying to reach the mantle chose the ocean as their drilling site. Under the continents, the crust thickens substantially. The average under a stable continent is somewhere between 30 and 50 kilometers. And under the great mountain ranges, under the towering weight of ranges like the Himalayas, the crust extends its roots downward to approximately 70 kilometers, pressed deep into the mantle, the way a loaded ship settles lower into water. The mountains you can see above the surface are matched by an invisible keel of thickened crust below. This is already a remarkable thing to hold in mind. The ground is not the same thickness everywhere. The floor of the world varies from the shallow shell beneath the Pacific Ocean to the deep crustal roots that anchor the highest peaks on Earth. And Mohorovičić found the evidence for all of it in the timing of waves from a single earthquake. Not by drilling, not by looking, by reading the clock. There is another layer distinction worth settling into here, because the terminology can become tangled in ways that obscure rather than illuminate, and a tangle is the last thing you need as you are finding your rest tonight. The crust and the mantle are chemical divisions. They describe what the rock is made of, its mineral content, its composition. But there is another way to divide the Earth's outer portion, and that is by mechanical behavior, by asking not what the rock is made of, but how it behaves under the conditions it encounters. And when you do that, you find a slightly different picture. The uppermost portion of the Earth, encompassing both the crust and the topmost part of the mantle just below the Moho, behaves in a brittle, rigid fashion. It forms the tectonic plates, the great moving slabs whose boundaries are where earthquakes happen and volcanoes erupt. This rigid outer shell is called the lithosphere, from the Greek for stone, and it is the layer that moves as a coherent solid. Below it, still within the upper mantle in chemical terms, lies a layer that is warmer and softer, not melted exactly, but sufficiently close to its melting point that it deforms plastically over long timescales. This is the asthenosphere, from the Greek for weak, and it is on this relatively mobile layer that the rigid lithospheric plates slide and drift, moving across the Earth's surface over millions of years. Think of it this way: if you put a slab of hard toffee on top of a jar of warm honey and pushed the toffee slowly sideways, the honey would yield and flow beneath it while the toffee remained rigid. The lithosphere is the toffee. The asthenosphere is the warm honey. The chemical boundary, the moho, cuts across this mechanical picture separating crust from mantle, but the mechanical boundary between rigid lithosphere and soft asthenosphere lies entirely within the mantle, some tens to perhaps 200 kilometers below the surface, depending on the local temperature. Two different ways of slicing the same onion, and both of them real. Mohorovičić had found the first of these hidden flaws, the moho, in 1909. It was a profound discovery. But in the decades that followed, the deeper questions remained. The mantle stretched downward for nearly 3,000 kilometers by the best estimates of the time. And below the mantle, if anything lay there at all, was entirely unknown. No wave had yet been coaxed into betraying what lay at greater depth. No careful comparison of arrival times had yet revealed a boundary deeper than the moho. The planet's interior, below the first few dozen kilometers, remained a sealed and silent question. What broke that silence was not an experiment, and not a new instrument, but a pattern of absence. A ring of quiet that spread across a great part of the planet every time a major earthquake struck, and that had been sitting in the records for years, noticed but not fully understood, waiting for someone to ask the right question about what it meant. And the man who asked that question, who stared into the deaf ring and read its shape and used it to draw a line 2,890 kilometers underground, was a German-American seismologist named Benno Gutenberg. Gutenberg was born in Darmstadt in 1889, the year Andrea Mohorovičić was already making the observations that would lead to the discovery of the moho. By the time Gutenberg came to his own great discovery, in 1913 he was 24 years old, working with the global seismograph records that were, by then, beginning to accumulate in useful quantities as stations spread across more of the world's surface. He was studying what happened to P waves from large earthquakes, tracking where they showed up and where they didn't, mapping the arrival patterns at stations distributed at various angular distances from the epicenters. An angular distance here means what you would measure if you drew a line from the earthquake through the center of the Earth and out the other side, then measured the angle at the center between the earthquake and a recording station. A station on the opposite side of the planet from an earthquake sits at 180 degrees, 1/4 of the way around the Earth sits at 90 degrees. And Gutenberg noticed, working through his records, that in a band from roughly 103 degrees to about 142 degrees from any major earthquake, the strong direct P waves simply did not arrive. They were absent. The seismographs in that band, those at the right angular distance from the earthquake, recorded no primary wave at all. This is the shadow zone, and its existence, when you first encounter it, is puzzling enough that it demands a careful, unhurried explanation, because the explanation is the most elegant in all of seismology, and it is the direct path to understanding not just the outer core, but the way all of our knowledge of the deep interior was won. Consider first the S waves. We have already settled into the idea that S waves, the shear waves, the side-to-side movers, cannot pass through liquid because liquids have no shear strength, no resistance to sideways deformation. You can push a liquid down and it will resist that compression, which is why P waves, compressional waves, can pass through water and liquid iron. But you cannot push a liquid sideways and have it spring back, which means a shear wave arriving at a liquid boundary is stopped, absorbed, extinguished. There is nowhere for its energy to go in that direction. After a major earthquake, if you map the positions of every seismograph on the planet and note which ones record the S-wave, a clear pattern emerges. Up to about 103 degrees from the epicenter, the S-waves arrive. They have traveled through the solid mantle, bending slightly as they go because the mantle's properties change with depth, but arriving recognizably and on schedule. And then beyond 103 degrees, they simply stop, not gradually, not fading over a range. Beyond that angular boundary, no direct S-wave arrives anywhere on the rest of the planet. The far side goes silent. There is only one physical explanation for that silence. Somewhere along the path those waves were trying to travel, they ran into something liquid, something with no shear strength, something that absorbed the sideways energy of the shear wave and refused to pass it on. And given the geometry of the Earth, given the way waves travel through a sphere, the depth of that liquid boundary can be calculated from the angle at which the S-wave silence begins. Gutenberg did that calculation. The boundary came out at approximately 2,090 kilometers below the surface. Let that depth sit with you for a moment. Nearly 3,000 kilometers down. The Kola super-deep borehole, that monument to human ambition and geological stubbornness, reached 12.36 kilometers before surrendering. The boundary Gutenberg found from his 1913 records lies more than 200 times deeper than the deepest hole we have ever dug. He found it not by digging, but by listening to a silence. The P-wave shadow zone is slightly more complicated in its geometry, and perhaps even more instructive in what it reveals. P-waves can cross liquids, as we have established, and they do cross the liquid outer core. But a wave crossing the boundary between the slower solid mantle and the slower still liquid outer core does something that any wave does when it crosses into a different medium. It bends. Its path curves, refracts, just as a beam of light bends when it passes from air into glass or water. The amount of bending depends on how different the two materials are. At the core mantle boundary, P waves entering the liquid outer core are sharply refracted inward, their paths bending significantly away from the surface of the planet and toward the center. This sharp bending, when you trace the geometry of many waves entering at many angles, creates a zone of deficiency on the far side of the planet, a range of angles between about 103 and 142 degrees where the refracted P waves do not emerge. They are deflected away from that ring, sent either too far inward or bent back out at steeper angles that emerge beyond 142 degrees. The shadow zone is the geometric consequence of the bending, a region of relative quiet created by the physics of wave refraction at a boundary between materials of very different properties. And the width of that shadow zone, the precise arc from 103 degrees to 142 degrees, is a measurement. It encodes, in its geometry, the size and depth of the core. Gutenberg used it. He traced the edge of the P-wave shadow, calculated the refraction angles implied by that edge, and worked backward to the depth and approximate size of the boundary that would produce exactly that pattern. The answer was approximately 2,090 kilometers. The core mantle boundary, the Gutenberg discontinuity as it is now called, lies at that depth, and modern seismology has refined the number to approximately 2,190 kilometers, a figure sitting in remarkable agreement with what a 24-year-old man deduced from the records available to him in 1913. That number, 2,090 kilometers, marks what is arguably the most dramatic boundary inside the entire planet. Not the Moho, significant as it is. Not the inner core boundary we will come to in a moment. The core mantle boundary is a sharper transition than almost anything else Earth contains. On one side of that boundary lies the silicate rock of the lower mantle, dense and hot, and composed of minerals with long names that describe precise atomic arrangements of silicon, oxygen, magnesium, and iron. On the other side lies liquid iron, churning and metallic and about as different from silicate rock as any material on Earth can be. The jump in density across that boundary from lower mantle rock to liquid outer core is greater than the jump you would find walking from solid granite at the surface directly out into the open air, greater than rock to air. And it sits 2,090 kilometers below where you are lying right now. The silicate world and the metal world, separated by a boundary that no instrument has ever touched, that no probe has ever crossed, that we know as well as we do only because of the shape of a silence, the angle of a deaf ring spreading across the planet's surface every time a great earthquake shakes the ground. Gutenberg in 1913 had, without any intention of doing so, drawn the most important line on a map of the interior of the Earth. He had separated the world into two great regions. Above 2,090 kilometers, the silicate realm, crust, mantle, the familiar rocky planet. Below 2,190 kilometers, something else entirely, a metallic world of liquid iron on a scale almost impossible to imagine, a sphere within a sphere, churning in the dark under pressures and temperatures that bracket anything in ordinary experience. And the fact that he found it from the absence of waves, from a ring of quiet spreading across the planet's seismographs, from the silence in the data, rather than from any signal present in it, tells you something essential about the whole enterprise we are following tonight. We map the unreachable not by what we can detect, but often by what we cannot. Not by the signal, but by its absence. Not by what the wave tells us as it arrives, but by what its failure to arrive reveals about the world it tried to cross. This is a form of knowledge that requires patience and a certain willingness to trust in the negative, to believe that a missing reading is as meaningful as a present one, and perhaps more so. Gutenberg would live until 1960, long enough to see his 1913 calculation confirmed and refined, long enough to watch seismology mature from a collection of paper records spread on desks into a global discipline with stations on every continent. He had found the outer boundary of a liquid metallic sphere sitting at the planet's core, and for more than 2 decades after his discovery, the model of the core was simple, a single ball of liquid iron, featureless, undivided, a metallic ocean at the center of the world. And then someone found a disturbance in that ocean. Someone found waves arriving inside the zone where nothing should arrive, and in doing so, found something hidden within the hidden, a world inside the world that no one had known to look for, that someone worked largely alone. She sorted her data not on banks of computers, not with teams of graduate students, but on cardboard cards, which she kept organized in oatmeal boxes. And she made one of the most consequential discoveries in the history of geophysics on the basis of faint signals that almost everyone else had overlooked or dismissed as instrumental noise. Her name was Inga Lehmann, but that story belongs to the movement that follows. For now, let the shadow zone settle. Let the image of the deaf ring sit quietly in your mind, the wide arc of the planet's surface that falls into seismic silence after every great earthquake. The ring that held, encoded in its silence, the precise depth of a boundary nearly 3,000 kilometers underground. The boundary between the silicate world and the metallic one. The line that Gutenberg drew from paper records in 1913. Outside, wherever you are, the ground beneath you is three-dimensional in a way we rarely think about. The crust under your feet, whether it is the relatively thin floor of an ocean basin or the deeper root of a continent, sits atop the Moho, that first hidden floor that Mohorovičić found from the early arriving waves of a Balkan earthquake. And far below the Moho, below kilometers upon kilometers of hot silicate mantle, lies the core mantle boundary, the Gutenberg discontinuity, where rock gives way to metal and solid gives way to liquid. 2 boundaries, 2 discoveries, separated by 4 years and by the work of 2 men who were, in their different ways, doing the same thing, asking why the waves were not behaving as expected and following the answer into the dark. Mohorovičić found his boundary because a wave arrived too quickly, because it had sped up in something denser below, and those extra kilometers of faster travel brought it to the surface ahead of schedule, like a traveler who found the road. Gutenberg found his boundary because waves stopped arriving at all, because a ring of the planet went deaf, and the shape of that deafness described the thing that had silenced it, a liquid core, a vast metallic ocean, 2,090 kilometers underground. Two discoveries, two silences in their way. One, the silence of an unexpected early arrival that implied a hidden flaw. One, the literal silence of the deaf ring, the shadow zone, the blank arc of seismographs that heard nothing. The Earth has a way of communicating its deepest secrets through these subtle distortions of expectation, these moments when the careful observer says, quietly, "That is not what I expected," and then has the patience to follow the thought wherever it leads. And as the night deepens, and as your breathing settles further into a slower rhythm, it is worth letting the scale of all this become something not anxious, but simply vast, simply wide. The mantle is not a thin layer. It extends from the base of the crust all the way down to the Gutenberg discontinuity, nearly 2,900 kilometers. That is more than the distance from New York to Los Angeles, but imagined not as a horizontal journey across the surface, but as a vertical descent directly downward through rock that grows hotter and denser with every kilometer, through pressures that rise steadily as more and more of the planet's mass presses down from above. A descent through which no human instrument has traveled, a distance known only through the timing of waves. The mantle is not empty or uniform. It has its own structure, its own variations, regions where wave speeds are slightly higher or lower, places where slabs of cold ocean floor are sinking downward from the surface and carry their chill into the deep, places where hot material rises slowly toward the base of the plates. All of this becomes visible in the only way it can become visible, through the patience of seismology, through the accumulated records of thousands of earthquakes recorded at thousands of stations, through the slow work of building from those records a picture of what the waves encountered on their journey. That picture has grown considerably more detailed since 1913, and we will come to the modern version of it. But for now, the two foundational lines have been drawn. Mohorovičić drew the first one, separating crust from mantle, in 1909. Gutenberg drew the second one, separating mantle from the liquid outer core, in 1913, both from waves, both from timing and from the shape of arrivals and absences, both from the patient reading of lines on paper. And below the second line, deeper than Gutenberg's boundary, deeper than the liquid outer core whose existence the shadow zone had proved, lay a question that the 1913 model left open. A metallic ocean at the center of the Earth, liquid, churning, featureless. That was the picture. It was consistent with the evidence. It would remain the accepted picture for more than 2 decades. Until, on a quiet day, sometime in the early 1930s, Lehmann noticed that some of the waves she was looking at were showing up where the accepted picture said they could not possibly be. She was Danish, born in 1888 in a suburb of Copenhagen, and she had come to seismology by a route that was not entirely direct. She had studied mathematics and physics, had worked briefly in other fields, and had come eventually to the study of earthquake records with the Danish Geodetic Institute, where she spent decades as the institution's chief seismologist, responsible for the installation and management of seismograph stations across Greenland, among other places. She was, by all accounts, meticulous, somewhat reserved, and possessed of a quality that in science sometimes matters more than raw brilliance. She did not let uncomfortable data go unexplained. The data that troubled her was this. After large earthquakes, when she mapped the pattern of P-wave arrivals around the planet, she found that within the shadow zone, in that ring between roughly E103 and 142 degrees, where P-waves were supposed to be absent, Some stations were recording faint P-wave arrivals, not strong arrivals, not the clear, decisive signals that arrived at stations outside the shadow zone. But something, faint traces on the records arriving at times that were, if you accepted the existing model of a single liquid outer core, simply impossible. Now, one response to an anomalous reading in any scientific field is to assume the instrument is at fault, equipment misbehaves, records contain noise. Faint, anomalous signals are easy to attribute to vibrations from a passing train, or to imperfect calibration, or to any number of mundane causes that have nothing to do with the deep interior of the Earth, and it is likely that many people who saw similar faint arrivals in their records dismissed them on precisely those grounds. The existing model was consistent with everything else. A few faint and strange arrivals were easy enough to set aside. Lehmann did not set them aside. She gathered more cases. She looked at multiple large earthquakes, multiple stations, multiple records. And the faint arrivals were there in enough of them, in enough different locations, and from enough different events, that she became convinced they were real. They were not instrument noise. They were actual P-wave energy arriving inside the shadow zone where no P-wave should be. And if they were real, they needed an explanation. She sat with the oatmeal boxes and the cardboard cards, the physical sorting system that she had developed for managing the enormous quantity of paper records that the monitoring network generated, and she worked through the possibilities. If the outer core was entirely liquid, as Gutenberg's model assumed, then P-waves entering that liquid sphere would be refracted inward and would emerge on the other side of the planet outside the shadow zone, exactly as observed. None would emerge within the shadow zone. The geometry was clear and it matched almost all the data, but not quite all of it. Lehmann's reasoning was this. What if the liquid outer core was not the deepest thing? What if, inside the liquid outer core, there was a second, smaller sphere with different properties, a sphere whose boundary would reflect or refract some of the P-wave energy back outward, sending it on a different path that brought it back up to the surface within the shadow zone? If such an inner sphere existed, and if it had higher wave speeds than the surrounding liquid, then some waves that entered the outer core and headed toward this inner boundary would be partially reflected or bent back, and those reflected or refracted waves would travel a path that brought them through the shadow zone and up to the surface as the faint arrivals Lehmann was seeing. She calculated what properties such an inner sphere would need to have to produce the arrivals she was observing. She worked out its approximate depth, and in 1936 she published her findings in a paper that ran to just a few pages and bore the minimalist title that has since become something of a legend in the field. The paper was called simply P', written as P with an apostrophe after it, the notation at the time for P waves that had traveled through the core. In those few pages, Lehmann argued quietly and with the precision of someone who has been over the same ground many times to be sure of her footing, that the Earth had a solid inner core sitting inside the liquid outer core, and that the boundary between them was located at approximately 5,250 kilometers below the surface. The paper was not received with immediate universal acclaim. Science rarely works that way. But it was taken seriously, it was tested by other researchers using other data from other earthquakes, and over the years that followed it was confirmed. The model of the core as a single liquid ball gave way to the model we hold today, a solid inner core wrapped in a liquid outer core, the two of them together making up the deepest part of the Earth, the metallic heart around which the silicate mantle turns. The boundary that Lehmann found, the surface between the liquid outer core and the solid inner core, is called the Lehmann discontinuity, or the inner core boundary. It sits at approximately 5,150 kilometers depth. The inner core it encloses has a radius of about 1,220 kilometers. To put that in terms that might settle more comfortably in the mind, Our moon has a radius of about 1,537 kilometers. The inner core is roughly 70% as large as the moon, a solid sphere of iron sitting at the center of the world, hot beyond anything at Earth's surface, pressed into solidity not by cold, but by the immense and unceasing weight of everything above it. Because the inner core is not solid because it is cold, that is perhaps the most important and counterintuitive thing about it, and it is worth sitting with. At the surface of the Earth, iron melts at about 1,138 degrees Celsius. The inner core, by the best current estimates, sits at temperatures of roughly 5,000 to 5,400 degrees Celsius. By every surface standard, by every intuition built from the behavior of iron on a laboratory bench, that temperature should produce liquid metal, not solid. At 5,200 degrees, iron at normal pressure would not merely be melted but would be partially vaporized. And yet the inner core is solid. The reason is pressure. Temperature is not the only thing that determines whether a substance is solid or liquid. Pressure matters enormously. As you compress a material, you force its atoms closer together. You increase the energy required to break the ordered arrangement of a solid, and let the atoms flow freely as a liquid. You raise the melting point. The inner core, sitting at the center of a planet with a radius of 6,371 kilometers, bears the weight of everything above it, the entire outer core, the entire mantle, the entire crust, all pressing inward from every direction. The pressure at the center of the Earth reaches approximately 360 gigapascals. A gigapascal is 1 billion pascals, and atmospheric pressure at sea level is about 0.1101 gigapascals. The center of the Earth is at roughly 6 million times the pressure you are experiencing as you lie, reading or listening tonight. Under that pressure, the melting point of iron is driven far above the local temperature. The iron cannot melt because it cannot afford to. The pressure will not permit it. Solid by squeeze, not by cold, a sphere hotter than the surface of the sun, held rigid by force alone. And Inga Lehmann found it. Working alone with cardboard cards in oatmeal boxes, reading faint lines on paper records from earthquakes on the other side of the world, she found a world inside the world that no one else had known to look for, and she published her evidence in 1936 in a paper short enough to read in an afternoon. She lived until 1993, reaching the age of 104, long enough to see her discovery not only confirmed but refined by technology she could not have imagined. In the 1930s, she saw the inner core boundary become a standard feature of every Earth model. She saw the oatmeal box era give way to digital records and global networks and computers sorting in milliseconds what had taken her weeks. And through all of it, the discovery was hers, built from the patience to ask why faint waves were appearing when no wave had any right to be. There is a quiet instruction in that for anyone who is paying attention. The most revealing signals are sometimes the faint ones that don't fit, the anomalies that everyone else has set aside, the waves that should not be there. Lehmann kept hers, sorted them carefully, and found the solid heart of the world. So now the structure is laid in place. The moho found by Mohorovičić in 1909 from waves that arrived too early, marking the base of the crust at depths ranging from 5 kilometers under the oceans to 70 under the great mountain ranges. The Gutenberg discontinuity found by Gutenberg in 1913 from the shadow zone, the deaf ring that proved a liquid layer beginning at 2,090 kilometers, a density boundary greater than rock to open air. And the Lehmann discontinuity found by Lehmann in 1936 from faint waves inside the forbidden zone, marking the surface of a solid inner core at 5,050 kilometers, a sphere 70% the size of the moon, solid under unimaginable pressure. 3 lines drawn into the dark by 3 people listening to waves, 3 discoveries that together built the architecture of the world beneath your feet. And each of them found, not by going there, not by measuring anything directly, but by reading the distortions that the hidden interior imposed upon the waves passing through it. The crust, the mantle, the liquid outer core, the solid inner core, a map of a place no one will ever visit, assembled from timing and from silence. The night is quiet around you. The seismographs in their still rooms are quiet too for now, waiting, their needles patient in the dark. Somewhere, perhaps, a small tremor is moving through the mantle, far beneath the ocean floor. Not enough to wake anyone, not enough to be felt at the surface, but enough to make a faint line on a record somewhere, a line that a careful reader might someday use to refine still further the picture of what lies below. The work of mapping the unreachable is never quite finished. Every new earthquake is another message from the interior, another set of wave arrivals to be read, another chance to ask the question that has driven this whole story. The wave should have arrived by now. Why hasn't it? And what does its silence tell us about the rooms it tried to cross? For a long time, the picture was incomplete in a way that troubled the people who studied it most carefully. The shadow zone was understood. The S-wave silence beyond 103 degrees of arc had been explained, and Benno Gutenberg had used the edge of the P-wave shadow to measure the core mantle boundary with a precision that still astonishes anyone who knows how little he had to work with in 1913. The outer core was liquid. That much seemed settled, in the way that things seem settled in science when the evidence is consistent and the explanation elegant, and no one has yet looked closely enough to notice that something small is wrong. The something small was this: there were waves arriving where no waves should have been. Not everywhere, not obviously. In most of the shadow zone, that band of the planet's surface stretching from roughly 103 degrees to 142 degrees away from any given great earthquake, the records were quiet in the expected way, the P-wave arrivals faint or absent, the S-waves gone entirely. But in a narrow region deep inside the shadow at certain stations, certain seismographs registered faint P-wave signals that the liquid core model could not account for. They were not strong signals, they were easy to dismiss, easy to attribute to instrument error, or to some quirk of local geology near the recording station. Most people who noticed them set the anomaly aside. The model was so clean, so explanatory, so well supported by everything else, that the case for ignoring a few weak and inconvenient arrivals was genuinely strong. One person did not ignore them. Inge Lehmann was a Danish seismologist born in 1888, working in Copenhagen, and she had spent years doing the unglamorous work of earthquake data processing, collecting arrival time records from stations across Europe and beyond, checking the numbers, logging the times, building the empirical picture of wave behavior that the whole field depended on. The work required patience of a kind that is almost difficult to describe to someone who has not done it. Sitting with paper records, reading faint lines traced by needles, responding to vibrations from earthquakes that had happened thousands of kilometers away, sometimes weeks before the record arrived, and attempting to extract precise timing from tracings that were often smeared or contaminated by other signals, or simply too faint to be certain. And doing this not for one earthquake, not for 10, but for hundreds, cataloguing the results, comparing them, looking for the patterns that only emerged when you had enough data to average out the noise. She kept the records on cardboard cards. The cards went into boxes, and the boxes, by her own later account, were oatmeal boxes, the cylindrical kind, repurposed into a filing system for the records of the planet's trembling. It is one of the more quietly remarkable images in the history of science. A woman in Copenhagen, in the years between the two world wars, mapping the deep interior of the Earth with a system of cardboard and oatmeal boxes in a field that was still finding its footing, with instruments that were improving but had not yet achieved the sensitivity that later decades would bring, and with almost none of the computational assistance that a modern seismologist would consider the bare minimum for the work. And she noticed the waves that should not have been there. The question, once she decided to take them seriously rather than dismiss them, was what could produce a P-wave arrival inside the shadow zone? If the outer core were a single uniform sphere of liquid, then P-waves entering it from any angle would refract, bend in ways that deflected them around and away from that forbidden band. The mathematics of refraction through a liquid sphere of the known size and approximate density did not leave room for P-waves to turn around and emerge inside the shadow. They were not supposed to be there. They could not be there if the simple liquid sphere model was correct, but they were there. They were. Lehmann turned the problem over. She worked at it not in the way that makes for dramatic stories, not with a single night of inspiration, not with a moment where the solution arrived complete, but in the patient, grinding way that most real scientific progress actually happens, examining the data from different earthquakes, checking whether the anomalous arrivals were consistent, whether they appeared at similar angular distances from multiple epicenters, whether they had the timing, characteristics you would expect from waves that had traveled a particular path. And gradually, methodically, she built the case for an explanation that was at once simpler and more astonishing than any alternative. There was something inside the liquid outer core, a sphere within the sphere, a region at the center, denser or more rigid in some way, that could act as a reflector or refractor for P-waves, bending some of them back upward and outward at angles that would carry them, unexpectedly, into the region of the surface that was supposed to be silent. If there were a solid inner core, a sphere inside the liquid with different wave speed properties, then P-waves that struck its surface would partly reflect back and partly refract through it at changed angles. Some of those refracted and reflected waves would re-emerge from the liquid outer core and travel upward to the surface at exactly the angles required to arrive inside the shadow zone. The anomalous arrivals were not noise. They were not instrument error. They were messages, very faint, from a structure no one had known was there, a solid heart at the center of the liquid outer core. She published the idea in 1936 in a paper she titled simply P, pronounced P prime, a notation for a particular class of P-wave arrivals that had passed through the core. The paper was short, it was precise. It made a prediction that could, in principle, be tested. If there was a solid inner core at a specific depth, then P arrivals should appear at consistent angular distances from earthquakes, with timing that matched the geometry of reflection and refraction off that inner surface. The prediction was correct, the solid inner core was real. The boundary she had found, the surface of that inner sphere, sits at approximately 5,150 kilometers below the surface of the Earth. It carries her name, the Lehmann discontinuity. And the discovery is one of the stranger ones in the record because it required two things that do not always arrive together: the willingness to take seriously a signal that almost everyone else had set aside, and the computational and reasoning capacity to work out what that signal implied. Working alone, with paper records and cardboard and oatmeal boxes, in a period when the tools available for the job were a fraction of what would later exist. Inga Lehmann lived to be 104 years old, dying in 1993, which means she lived long enough to see seismic tomography transform the field she had helped build, long enough to see the inner core she discovered confirmed and refined by decades of data from thousands of earthquakes and hundreds of recording stations around the world. She was awarded the William Bowie Medal of the American Geophysical Union in 1971, one of the highest honors in geophysics, and she continued to publish scientific papers into her 80s. But the work that will always carry her name is the work done in Copenhagen in the 1930s with cardboard cards in oatmeal boxes, finding a solid sphere at the center of the world. Consider for a moment what that inner core is. It has a radius of approximately 1,220 kilometers. To give that number some purchase on the imagination, The Moon has a radius of about 1,137 kilometers. The inner core is roughly 70% of the size of the Moon, a sphere of that scale sitting at the absolute center of the Earth, surrounded on all sides by the liquid outer core, which in turn is surrounded by the vast thickness of the mantle, which is capped by the thin crust on which we live. It is an enormous thing, and it has been there for what is thought to be billions of years, and until 1936 no human being knew it existed. And it is solid. That fact requires a moment to sit with, because the instinct is to assume that anything as hot as the inner core must be liquid, must be molten, must be in the same state as the liquid outer core that surrounds it. The temperature at the boundary between the inner and outer core, the Lehmann discontinuity, is estimated at roughly 5,000 to 5,400 degrees Celsius. The title of this narration offers the figure of approximately 5,200 degrees, and that sits comfortably within the range that the evidence supports. To put that in perspective, the surface of the Sun, that roiling visible face of the star at the center of our solar system, has a temperature of about 5,500 degrees Celsius. The boundary of the inner core is almost as hot as the surface of the Sun, and yet the material there is solid, not liquid. Solid iron compressed into a crystal structure, maintaining the rigid geometry of a solid rather than the mobile, flowing geometry of a melt. How is that possible? The answer is pressure. The deepest intuition about phase transitions, about why things melt or freeze, is that temperature is the deciding factor. Heat something enough and it melts, cool it enough and it freezes. And this is generally true, but it is not the whole truth. Pressure also matters. At high enough pressures, the melting point of a material, the temperature at which it transitions from solid to liquid, rises. The atoms are being squeezed together with such force that even at temperatures far above what would melt iron at the surface, they cannot achieve the looser, more mobile arrangement of a liquid. The pressure will not permit it. It forces the structure to remain rigid, even as the thermal energy pounds against it. At the center of the Earth, the pressure reaches approximately 360 gigapascals. A gigapascal is itself an enormous unit, 1,000,000 times the pressure of Earth's atmosphere at sea level. 360 gigapascals is therefore roughly 3.6 million times the atmospheric pressure you and I are sitting in right now, in the quiet of the room, in the dark. Under that pressure, iron's melting point has been pushed up high enough that even at 5,200 degrees Celsius, it remains solid. The inner core is not cold, it is solid by compression, not by coolness, held rigid not by the absence of heat, but by the overwhelming weight of everything above it, pressing down across 6,170 kilometers of rock and liquid metal. The entire mass of the planet, from crust to outer core, is bearing down on that central sphere, and the sphere holds its shape because there is no alternative. There is nowhere for it to go. There is nothing that can relieve the pressure. It is pinned into solidity by the sheer enormity of the planet resting on it. This is one of those facts that the mind encounters and temporarily loses its footing on, the way you might lose your footing on a path that looked solid and turned out to be steeper than you thought. The center of the Earth is hotter than the surface of the Sun, and it is solid. Both of those things are true simultaneously. The universe does not always behave in the way our surface-level intuitions predict, and this is one of the places where the gap between intuition and reality is particularly wide and particularly worth pausing to feel. Now, what is the inner core made of, and what is the mantle and the outer core? What are the actual materials involved, not just the mechanical states, but the substances, the chemistry? Begin with the mantle, because the mantle is by far the largest structure inside the Earth. It extends from the Mohorovičić discontinuity, the Moho, at perhaps 30 to 50 kilometers down under the continents, all the way to the Gutenberg discontinuity at 2,090 kilometers. A thickness of nearly 2,900 kilometers making up roughly 84% of Earth's total volume. The dominant minerals in the upper mantle are silicates, compounds built around silicon and oxygen, with significant amounts of magnesium and iron woven in. The most familiar of these, at least by name, to anyone who has spent time near volcanoes or looked at geological samples, is olivine, a greenish silicate mineral that crystallizes in the upper part of the mantle and is carried to the surface in various volcanic contexts. Alongside olivine, pyroxene minerals make up much of the upper mantle's fabric, contributing to the dense, heavy rock that underlies the thinner and lighter material of the crust. But as depth increases as the pressure rises and rises, olivine and pyroxene cannot maintain their familiar crystal structures. The atoms are squeezed into new arrangements, higher pressure phases in which the same chemical constituents pack together differently, more densely, more efficiently in response to the crushing weight above. The most important of these high-pressure phases, and the one that carries what is perhaps the most striking distinction in this entire story of the Earth's interior, is a mineral called bridgmanite. Bridgmanite is not a name most people know. It was not a name anyone knew until 2014, when the mineral, which had been synthesized in laboratories and studied intensively for decades under the provisional name magnesium silicate perovskite, received its official designation from the International Mineralogical Association. It was named for Percy Bridgman, an American physicist who spent much of his career studying the behavior of materials under extreme pressures and who received the Nobel Prize in Physics in 1946. The naming came late because bridgmanite had never been found in a natural sample at the surface in a stable, certifiable form. It exists only under the pressures of the deep mantle, and material brought to the surface by volcanic processes converts to other mineral forms before it can be identified. It took an unusual set of circumstances, a meteorite impact in Australia that preserved tiny amounts of the mineral in a shocked rock sample, to finally allow the naming to proceed. And bridgmanite is, by volume, the most abundant mineral on Earth. It makes up a large fraction of the lower mantle, and the lower mantle is the largest single region inside the planet. Most of the solid rock in the world, most of the material of this planet by volume, is bridgmanite, a mineral that has no official scientific name until 2014, that no human hand has ever held in a stable natural form at the Earth's surface, that exists in a form we can observe only fleetingly, under laboratory conditions, in tiny samples squeezed between the faces of diamonds. The most common thing in the world, hidden. Below the mantle, at the Gutenberg discontinuity, the material changes fundamentally. The mantle's silicate rock, all those magnesium iron minerals, gives way to the core. And the core is not rock. It is metal. It is predominantly iron with a substantial admixture, somewhere in the range of 5 to 10%, of nickel. Iron-nickel metal, dense and dark, constituting the outer core in liquid form and the inner core in solid form. But here is a subtlety the seismic data revealed, one of those places where careful measurement unsettles a simple picture. The density of the core, as inferred from the speeds at which waves travel through it, and from the overall mass and gravitational behavior of the Earth, does not quite match what you would expect from pure iron-nickel. It is slightly less dense than pure iron-nickel should be, given the pressures involved. Something is lowering the density. Something lighter than iron is present mixed into the metal. What that lighter component is has been a matter of considerable scientific attention and some remaining uncertainty. The leading candidates include sulfur, oxygen, and silicon, elements that are abundant in the solar system and that, under the extreme conditions of the core's formation and long history, could have dissolved into the iron-nickel melt. The exact proportions and which of these elements dominate are still being worked out through a combination of seismic constraints and high-pressure laboratory experiments. The core is iron-nickel plus something, the something being one of the remaining open questions about a structure we cannot visit and cannot directly sample. This is worth staying with for a moment. We know the outer core is liquid because the S waves stop. We know its depth because of the shadow zone. We know its approximate density because of the wave speeds and Earth's mass. We can narrow down its composition by comparison with laboratory measurements of how iron-nickel alloys behave under pressure. But the exact recipe, the precise chemical fingerprint of the liquid metal 3,000 kilometers below your feet, is still being refined, still being argued over by people who spend their careers making tiny samples in diamond anvil cells and comparing the results to the seismic record. The map of the interior is extraordinarily detailed by any standard, and it is still incomplete. Both things are true. Now consider what the liquid outer core does apart from existing. The outer core is in motion. Liquid iron heated from below by the inner core and from within by the slow decay of radioactive elements rises and falls in convection currents, the same basic process by which water in a pot moves when it is heated on a stove, with warmer material rising and cooler material sinking, creating circulation. But the outer core is not a pot of water on a stove. It is a shell of liquid metal, thousands of kilometers thick, rotating with the planet as the Earth turns, and the combination of convection and rotation produces something that a pot of water never can. It generates a magnetic field. The mechanism by which a moving electrically conductive liquid generates a magnetic field is called the geodynamo. Think of it by analogy with a much simpler device, an electrical generator, where a conductor moving through a magnetic field generates an electric current, and an electric current in turn generates a magnetic field. In the outer core, the liquid iron is the conductor. The rotation of the Earth provides the organizing geometry, and the convective motion provides the movement. The interaction of these factors, moving conductive fluid in a rotating system, sustains a self-reinforcing loop of electrical currents and magnetic fields that fills the space around the Earth and extends far out into space. This is the magnetic field that compass needles align with. This is the field that causes the northern and southern lights, the aurora borealis and aurora australis, by channeling charged particles from the solar wind down into the polar atmosphere. This is the shield that deflects the constant stream of charged particles the sun emits, the solar wind that, without the protection of the magnetic field, would erode the atmosphere and make the surface far more hostile to the chemistry of life than it currently is. The field generated by liquid iron moving in the outer core 3,000 kilometers below the surface is one of the things that makes the surface habitable. The geodynamo is not an abstract piece of geophysics. It is, in a very direct sense, part of the reason anything is alive up here to wonder about it. And the geodynamo runs on the heat of the inner core. As the Earth slowly cools over geologic time, a process that has been ongoing for billions of years since the planet formed from the accretion of material in the early solar system, the inner core grows very slowly by a process of freezing. Liquid iron in the outer core, cooling under the enormous pressure, gradually crystallizes onto the surface of the inner core, adding to its volume at a rate of perhaps a few hundred meters per million years. That crystallization releases latent heat and drives some of the convection in the outer core that keeps the geodynamo running. The solid inner core and the liquid outer core are not simply layers sitting passively on top of each other. They are in a dynamic relationship, the inner core growing, releasing heat, stirring the liquid above it, which moves and generates the field that blankets the surface. The center of the Earth is not quiet. It is, in a very slow and deep way, alive. The person who found the solid inner core, Lehmann, working with her oatmeal boxes in Copenhagen, could not have known all of this. The geodynamo, the crystallization, the slow growth of the inner core. What she knew was that some P waves were arriving inside the shadow zone and that the most reasonable explanation was a solid sphere at the center. The full meaning of that sphere, dating its role in the planet's magnetic history, in the thermal evolution of the core, in the long story of Earth as a system, would take decades more to develop through work by many people using instruments and techniques that did not exist in 1936, but the discovery was hers. The boundary is named for her. And there is something quietly apt about the fact that Lehmann lived for a century and 4 years, that she was born in the era of horse-drawn carriages and died in the era of space telescopes, that she was working at her desk in Copenhagen in the same decade that radar was being invented, that the field she contributed to so significantly transformed almost beyond recognition in her lifetime, and that she was present for all of it. The inner core she found has been there for billions of years, solid and patient at the center of everything. She was patient too in her way, patient with the data, patient with the anomalous signals that other people had set aside, patient enough to sit with the problem until the answer came. By the middle of the 20th century then, the architecture of the Earth was largely established. The Moho, found by Mohorovičić in 1909. The core mantle boundary, the Gutenberg discontinuity, measured from the shadow zone in 1913. The Lehmann discontinuity, the inner core boundary, discovered in 1936. Crust, mantle, liquid, outer core, solid, inner core, the 4 great regions of the planet, each found not by drilling or by direct measurement, but by listening to the behavior of waves generated by earthquakes and noting where they slowed, where they bent, where they converted from one type to another, and where they failed to arrive at all. The basic picture was right. What came later was refinement, an increasingly detailed and three-dimensional understanding of what the interior looks like, not just in cross-section, as a set of spherical shells, but as a complex, varied, lumpy reality in which temperature and composition and wave speed vary from place to place within each layer in ways that carry information about the history of the planet and the ongoing processes shaping it from within. And what came later, what came in particular from the 1970s and 1980s onward, was seismic tomography. It deserves its own careful attention, and the night is still long, and there is no reason to hurry. The word tomography comes from the Greek for slice, the same root as the medical procedure in which an X-ray source and detector rotate around a patient's body, taking images from many angles simultaneously, and a computer combines all those images into a three-dimensional reconstruction of the interior, a CT scan as most people know it. The principle of the medical CT scan and the principle of seismic tomography are, at a deep level, the same. If you can measure how a wave is changed by passing through a material from many different angles, you can reconstruct a three-dimensional map of the material's properties. In medical imaging, the waves are X-rays, the source is a controlled machine, and the detector is a ring that rotates in minutes. In seismic tomography, the waves are seismic waves. The sources are earthquakes happening all over the planet at unpredictable times and places, and the detectors are seismographs in permanent monitoring stations distributed across every continent. The reconstruction takes not minutes but years, combining the accumulated records of thousands of earthquakes recorded at hundreds of stations, each measurement telling you something about what the wave encountered along its particular path through the planet. What you are measuring in seismic tomography is variations in wave speed. If a wave travels faster than average through some region of the planet, that region is probably colder, denser, or more rigid than the surrounding material. If it travels slower than average, that region is probably warmer, hotter, or softer, perhaps partially melted or of different composition, or simply at a higher temperature that reduces the rock's stiffness. By mapping where waves are faster and where they are slower across thousands of different paths through the interior, seismic tomography builds a three-dimensional image of the planet's thermal and compositional structure. a picture not just of the shells and boundaries, but of the texture within them. The results were, and continue to be, revelatory. One of the most striking things tomography revealed was the fate of old ocean floor. Plate tectonics, the process by which the surface of the Earth is divided into large rigid plates that move, collide, separate, and in some places dive beneath one another, had been established as the organizing framework of surface geology by the late 1960s. The places where one plate dives beneath another are called subduction zones. The Pacific Plate, for instance, dives beneath parts of South America and beneath parts of Asia, generating the earthquakes and volcanoes of the Pacific Ring of Fire. The diving plate is called a subducting slab, and the question of what eventually happens to it had been uncertain. Does it melt and assimilate into the mantle? Does it sink all the way to the bottom? Where does it go? Seismic tomography answered this at least partly. The subducting slabs show up in tomographic maps as regions of faster than average wave speed because they are cold, dense remnants of old oceanic crust and lithosphere, colder than the surrounding mantle, and their greater coldness and density means waves move through them more quickly, and the tomographic images show those fast, cold sheets sinking, not just to the upper mantle, not just to a few hundred kilometers, but continuing downward through the lower mantle, bending and deforming as the mantle's increasing viscosity slows their descent, some of them appearing to pile up and spread out near the core mantle boundary, others penetrating into the lowermost mantle. Plate tectonics does not stop at the transition zone between the upper and lower mantle. The plates go deep, very deep, and the history of the surface is written in slow motion in the wave speed maps of the interior. And at the very base of the mantle, in the thin layer just above the core mantle boundary, a layer sometimes called the D double prime layer, a notation that has stuck since the middle of the 20th century. Seismic tomography revealed something else. Two enormous structures that had no obvious explanation and that remain, even now, among the most debated features of the deep Earth. They sit at roughly the same depth, just above the core mantle boundary, at approximately 2,090 kilometers down, but on opposite sides of the planet. One is beneath the African continent, the other is beneath the central Pacific Ocean. Both of them appear in tomographic maps as regions where S-waves travel significantly more slowly than average, hence their technical name, large, low shear velocity provinces, or LLSVPs. They are large in a way that is difficult to convey. Each of them covers an area comparable to a continent. They are not thin films. They have vertical extent of perhaps 1,000 kilometers or more. They are, in terms of volume, among the largest coherent structures inside the planet. Informally, they have been given names. The one beneath Africa is sometimes called Tuzo, after the Canadian geophysicist J. Tuzo Wilson, who made foundational contributions to the theory of plate tectonics. The one beneath the Pacific is sometimes called Jason, after the seismologist Jason Morgan, whose work on hotspots and mantle plumes connected deep Earth dynamics to the surface, features we see in places like Hawaii and Iceland. Tuzo and Jason, two vast, slow, anomalous structures at the base of the mantle, mapped with considerable precision by the accumulated data of seismic tomography, their boundaries relatively sharp, and their interiors clearly distinct from the surrounding lower mantle. And they are not fully understood. This is one of the places where the map of the interior is detailed, but the interpretation is contested, where the data is good and the explanation is still being worked out. Are they chemically distinct from the surrounding mantle, remnants of ancient material, perhaps from the very early Earth, that have persisted at the base of the mantle for billions of years? Are they simply regions of elevated temperature, hot pools in the deep mantle fed by heat from the core below? Are they the source of the large volcanic hotspots at the surface, the mantle plumes that feed the volcanoes of Hawaii and Iceland, and the Afar region of East Africa? There is evidence pointing in several of these directions, and the current scientific consensus is something like they are probably both compositionally distinct and hotter than average, and they are probably connected to surface volcanism, and there is still a great deal to be sorted out. They are real, they are mapped, they are enormous, and they are, in the best possible sense, still mysterious. The kind of mystery that fits comfortably in a story told at the edge of sleep, because it is a mystery that does not demand an answer tonight, that can simply be felt as a fact about how large and strange and layered the planet is beneath you. Tuzo and Jason, sitting at the base of the mantle in the quiet dark, thousands of kilometers below the ocean, and the continents, vast and slow and not quite explained, while above them the thin plates of the lithosphere move their few centimeters per year. And above those the ocean moves in its currents, and above those the air moves in its weather. And above all of that you are lying still in the small warmth of your room, breathing slowly, and the planet is carrying you through its rotation. And the geodynamo is running in the liquid iron far below, generating the field that bends the solar wind away from everything alive on the surface. And somewhere in the network of seismic monitoring stations distributed across the continents and the ocean floors, a needle is waiting, patient, for the next message from the interior. And now we come to the numbers themselves. They are the figures most people reach for first when they think about the deep interior, the pressure, the temperature, the extremity of the conditions at the center of the planet. And there is a reason to have saved them for here rather than offering them at the beginning. Because a number without context is just a number, and a number with context is something else entirely. It becomes a measure of how far human inference can reach into places no instrument has ever touched. The pressure at the very center of the Earth is approximately 360 gigapascals. 360 gigapascals. A pascal is already a unit of pressure, the pressure exerted by a very small weight on a very small area, roughly the weight of an apple resting on a surface about the size of a postage stamp. A gigapascal is a billion of those, and 360 gigapascals is 360 billion of them, which works out to approximately 3.5 million times the pressure of the atmosphere. At sea level, the pressure you feel on your skin right now, without noticing, the pressure that is so ordinary to every living thing on the surface that we have no sense of it at all unless it changes. 3.5 million times that. If you took a cube of material and placed it under 360 gigapascals of pressure, you would compress it beyond anything that can be described by the comfortable physics of everyday experience. Rock does not behave like rock at those pressures. Iron does not behave like iron. The very relationships between atoms change, the distances between them collapse, the electron clouds that give materials their familiar properties deform and rearrange, and what emerges is something that has no direct counterpart on the surface of the planet, something that must be studied in the most extreme laboratory conditions that human ingenuity has so far managed to produce, and the temperature. At the boundary between the outer core and the inner core at the Lehmann discontinuity 5,150 kilometers down, the temperature is estimated at somewhere between 5,000 and 5,400 degrees Celsius. The center of the figure, up with the middle of the range that the best current science supports, sits at around 5,200 degrees, 5,200 degrees Celsius. The surface of the sun, the glowing outer atmosphere of the star that every living thing on this planet depends upon for its warmth, runs at approximately 5,500 degrees. The center of the Earth is within a few hundred degrees of the surface of the sun. Stop for a moment with that. Not to rush past it. The surface of the sun, the thing that is so bright you cannot look at it, the thing that will burn your skin in minutes if you lie unprotected under it on a summer afternoon, the thing that has been the definition of dangerous heat for the entire history of human experience. That is approximately how hot it is at the center of the planet you are lying on right now. And yet the inner core is solid. Not because it is cool, Salpi, it is not cool by any conceivable standard, but because the pressure is so immense, so far beyond anything experienced at the surface, that it raises the melting point of iron above the local temperature. Pressure changes the rules. At ordinary pressures, iron melts well below 1,000 degrees Celsius. But at 360 gigapascals, the iron at the center of the Earth cannot melt because the atoms are squeezed so tightly together that the thermal energies, the vibration and agitation that constitutes heat, is not enough to shake them free of each other. The iron wants to be liquid by temperature. The pressure says no, and the pressure wins. A sphere of iron at 5,000 degrees Celsius, held solid by squeeze alone, sitting quietly at the center of the world. But here is what must be said clearly, honestly, and without softening, because it is one of the most important things about this entire subject. Those numbers, the 360 gigapascals, the 5,200 degrees, were not measured by any instrument placed at the center of the Earth. No probe has been there, no thermometer, no pressure gauge. The numbers are inferences. They are our best current estimates, derived from the combination of two things: what seismic waves tell us about density and rigidity at various depths, and what happens in laboratories when materials are subjected to extreme conditions. The laboratory tool that makes this possible is called a diamond anvil cell. It is, in principle, a beautifully simple device: 2 gem-quality diamonds cut to fine points, pressed face-to-face against a tiny sample of material, a speck almost too small to see, with a force that concentrates the load to an almost impossibly small area. Diamond is the hardest natural material on Earth, hard enough to transmit the force without being crushed itself, and transparent enough that lasers can be directed through it to heat the sample while it is compressed. By squeezing that tiny speck between 2 diamond points and simultaneously heating it with a laser, researchers can, in a very small room, recreate in miniature the conditions that exist 5,000 or 6,000 kilometers underground, and watch what happens to the material, whether it melts, whether it transforms, what phase it settles into, how it conducts electricity, how sound moves through it. The results of those experiments, combined with the travel times of seismic waves at different depths, allow scientists to work backward. What combination of temperature, pressure, and composition would produce waves moving at exactly the speeds we observe? The answer to that question is the number we report as the temperature and pressure at depth. It is not a direct reading. It is a solution to a problem. And it is for that reason still subject to revision as better experiments and better seismic data refine the constraints. The honest position, and it is worth saying this clearly, is that our best estimates of the conditions at the center of the Earth carry uncertainties that would seem large by the standards of surface science. The temperature at the inner core boundary, for instance, has been estimated at various points in the literature at anywhere from 4,000 to over 6,000 degrees, with the current best estimate settling somewhere in the 5,000 degree range, depending on which experimental data and which seismic model you trust most. This honesty does not diminish the achievement, it deepens it, because what it means is that the numbers were not handed to us, they were reasoned toward carefully over decades by people working at the intersection of physics and geophysics and materials science, building a picture that keeps being refined as methods improve. The map of the deep Earth is not a fixed thing, not something that was completed at a date and then set aside. It is still being drawn. And nowhere is that ongoing drawing more vivid than in the technique that represents the current frontier of what we can see into the planet: seismic tomography. The name comes from the same root as medical tomography, the imaging technique that allows doctors to see the interior of a body by passing X-rays through it from many angles and reconstructing the three-dimensional structure from the patterns of absorption and transmission. In medical tomography, the patient lies still in a scanner, the X-ray source rotates around them, and a computer integrates thousands of measurements to build a cross-sectional image. The principle is the same in seismic tomography, but the scale is planetary. The patient cannot be made to lie still. The source of the waves is unpredictable, and the detectors are scattered across the surface of a sphere rather than arranged in a neat ring. The earthquakes happen when they happen, where they happen, and the seismographs record what they record, and then the work of reconstruction begins. What makes it work is numbers. Not one or two earthquakes, thousands of them over years and decades, radiating waves in all directions, passing through every part of the planet's interior, along every possible path, and being recorded at every station that happens to be in the right position to catch them. Each earthquake station pair gives you one measurement. The wave arrived this fast, which means the material it traveled through was this dense, this rigid, this warm. One measurement tells you almost nothing. 10,000 measurements begin to constrain. 100,000 measurements integrated and modeled and iterated against each other begin to reveal structure. The principle behind the imaging is that wave speed is not uniform through the mantle and core. Colder, denser, stiffer rock transmits waves faster. Hotter, softer, more mobile rock transmits them slower. So if a wave traveling a particular path arrives at a seismograph slightly earlier than expected, the material along that path was probably cooler and denser than average. If it arrives slightly late, the material was probably warmer and softer. By comparing the actual arrival times against predictions from a reference Earth model, a mathematical average, and mapping where waves are consistently fast and where they are consistently slow, seismic tomography builds a three-dimensional portrait of the planet's thermal and mechanical state. The images that emerge are unlike anything the simple four-layer model would suggest. The mantle is not a uniform shell of even temperature and composition, slowly and uniformly convecting heat from the core to the surface. It is lumpy, complex, full of structure that has accumulated over billions of years of geological history. There are regions where the mantle is colder than average, and if you follow those cold regions downward, you can often trace them to the great subduction zones at the surface, the places where old oceanic plates bend down into the earth and sink. In the tomographic images, those subducting slabs appear as bright curtains of fast-moving waves, the cold, dense remnants of ocean floor that has spent hundreds of millions of years accumulating at the bottom of the ocean and then begun its long descent. Some of those slabs sink and slow and pool in the transition zone, a region of the mantle between roughly 400 and 700 kilometers depth, where the crystal structure of mantle minerals changes under increasing pressure. Others seem to punch through the transition zone and continue their descent all the way toward the core mantle boundary, 2,890 kilometers down, where they flatten and spread and slowly warm and are eventually incorporated back into the convecting mantle. Watching this in a tomographic image, a curtain of cold ocean floor descending in near slow motion toward the base of the mantle, carrying the chemistry and the memory of the surface with it, is one of the more extraordinary things that the technique has made visible. It is plate tectonics seen from the inside. The surface process, the grinding and spreading and diving of the plates, reaches all the way down, its fingerprints visible in the thermal structure of the mantle for hundreds of millions of years after the original ocean floor was formed. And then there are the places where waves move slower than expected. The blobs that carry the informal names Tuzo and Jason, the large low shear velocity provinces, vast structures at the base of the mantle beneath Africa and the Pacific, where S-waves move measurably, unmistakably slower than they should if the mantle were uniform. They have been mapped in considerable detail now. Their edges are reasonably sharp, their heights reach hundreds of kilometers above the core mantle boundary, their widths are continental. They are among the largest structures in the interior of the planet, and they are, as has been said, still not fully explained. What can be said is what the seismic data shows. The material in those provinces transmits S waves more slowly than the surrounding mantle. Slower S waves mean lower rigidity, or higher temperature, or different composition, or some combination of all three. The debate among geoscientists is about which of these factors dominates. Some researchers argue that the provinces are primarily thermal, hot upwellings bringing heat from the core mantle boundary upward, and that the slow wave signal is mostly a temperature effect. Others argue that they are compositionally distinct, relics of ancient differentiation early in Earth's history, when the planet was molten and different materials settled into different regions, and that some of that early chemical structure has persisted for billions of years, carried around in the convecting mantle, but never fully mixed back in. The truth may be some of both. What is striking is that these enormous features at the base of the mantle, these structures larger than the continent of Africa, sitting quietly in the dark, thousands of kilometers below the ocean floor, are known to us entirely because of the behavior of waves that were generated by earthquakes at the surface that traveled through the planet along every possible path, and that arrived at distant seismographs a fraction of a second later than a model said they should. From those fractions of a second patiently accumulated over decades of global earthquake monitoring, 2 continent-sized provinces at the bottom of the mantle were identified, mapped, given names, and made objects of serious scientific study. They were not found by drilling, they were not found by sampling, they were found by listening carefully to the way the earth rang. There is something about this that deserves to be held for a moment before moving on. The entire technique of seismic tomography, the most detailed and sophisticated tool we currently have for imaging the planet's interior, is at its heart a refinement of what Andrija Mohorovičić did in 1909 when he noticed that some waves from a Balkan earthquake arrived faster than they should have. He was doing the same thing, comparing what he expected against what he observed, and reasoning about what kind of material could explain the difference. The scale is different, the mathematics is enormously more complex, the data volume is incomparably larger. But the essential act, listening to waves and asking what the planet must look like inside to make them travel the way they did, is the same. And now, briefly, before the descent towards sleep deepens further, there is one more human story worth telling. Not because it changes the science, but because it is part of the history of how this knowledge was won. In the late 1950s, a group of American scientists proposed something that must have sounded at the time either visionary or absurd, depending on your disposition. They proposed to drill through the ocean floor, through the thin oceanic crust, retrieve an actual sample of the mantle, to go in some sense where the seismic waves had been. Not to the center, not even close, but past the Moho, past the boundary that Mohorovičić had identified from indirect evidence decades earlier, and bring back a piece of what lay beneath. The project was called Project Mohole. The choice of the ocean floor was deliberate and scientifically sound. On land, the crust is thick, 30 to 50 kilometers at minimum, up to 70 under great mountain ranges. But in the deep ocean, the oceanic crust is thin, as little as 5 kilometers in places, and the Moho is correspondingly close to the surface. If you were going to drill to the mantle, the place to start was off the floor of the ocean, where the distance was shortest. The site chosen was off Guadalupe Island, near the Pacific coast of Mexico. The drilling was done from a vessel that had to remain stationary over a single point in open water, a technical challenge that required the invention of dynamic positioning, a system of thrusters and navigation tools to hold a ship precisely in place above a drill site miles below, in the presence of currents and wind. That technology, invented for Project Mohole, is now standard equipment on every deep-sea drilling vessel in the world. The drilling went ahead. They reached the sediment layer on the ocean floor. They drilled through it and into the basalt of the oceanic crust beneath, extracting core samples, cylinders of rock pulled up from depths no one had reached before. It was, in a quiet and undramatic way, a moment of genuine accomplishment. The project was working. And then, in 1966, Congress cancelled it. The funding was cut, a combination of cost overruns, political changes, competing priorities, and the general turbulence of that particular decade in American public life. The Moho was never reached. The mantle was never sampled directly. Project Mohole ended without achieving its central goal, though the drilling technology and the methods it developed went on to underpin decades of subsequent scientific ocean drilling that has transformed our understanding of the ocean floor and the geological record preserved in seafloor sediment. It is worth noting, because context matters, that Project Mohole existed in the same period as the space race, the same years when the United States and the Soviet Union were competing to be first in orbit, first to the moon, first beyond the atmosphere. There was, for a while, a parallel competition pointed in the opposite direction, not up and out, but down and in. The Soviet Kola superdeep borehole and the American Project Mohole were, among other things, expressions of the same Cold War impulse that produced Sputnik and Apollo. The impulse to go farther than anyone had gone before, to reach something no one had reached, to demonstrate national technical capability at the frontier of the possible. The space race had its moon landings. The downward race ended at 12.26 kilometers with a drill hole that had to be abandoned because the rock at the bottom had warmed to nearly 180 degrees Celsius and begun to flow, closing itself around the drill like something that did not want to be entered. The space race gave us photographs of the Earth from outside. The downward race gave us 12 kilometers of core samples and a profound lesson in the limits of direct access. And in that contrast, the moon landings versus the Kola borehole, the image of the Earth from space against the image of the drill hole from the inside. There is something quietly instructive about the nature of this planet. Space is, in a certain sense, open. Once you have propulsion and life support, the universe does not particularly resist you. The distances are enormous, the engineering is ferociously difficult, but the physics of spaceflight is forgiving in ways that the physics of drilling is not. The problem is getting there. Once you are there, you can move around. The interior of the Earth is different. It is not a matter of distance. The center of the Earth is only 6,371 kilometers away. In the scale of the solar system, it is trivially close, but it is sealed behind pressures and temperatures that no material humans have yet devised can withstand. The rock that contains it does not merely resist drilling. At some depth, it flows, and whatever you put into it is simply absorbed. There is no mechanism conceivable with any current technology that would allow a probe to survive the journey from the surface to the core. The interior of the Earth is not merely unreached. For any practical sense, it is unreachable. And so the waves remain, the seismic waves remain the only messengers. Every time a large earthquake occurs somewhere on the planet along the fault lines of the Pacific Ring of Fire, in the deep subduction zones of the Western Pacific, along the transform boundaries of the ocean floor, it sends billions of elastic waves propagating outward in all directions through the body of the planet. Those waves travel for 20 minutes or more to reach the opposite side of the Earth. Some of them have passed through every layer of the interior. Some have reflected off the inner core boundary and been reflected again off the surface and descended once more. Some have converted from P waves to S waves at boundaries and traveled the rest of their journey in a different mode. And all of them, eventually, arrive at a seismograph somewhere on the surface and move a needle, or deflect a laser, or change an electrical signal by amounts measured in millionths of a meter, and are recorded. From those records, the arrival times, the amplitudes, the waveforms, the presence and absence of particular phases, everything in this long night's narration has been drawn. The Moho that Mohorovičić found in 1909 the core mantle boundary that Gutenberg fixed at roughly 2,890 kilometers in 1913. The solid inner core that Lehmann found in 1936, working alone at her desk in Denmark, sorting cards in oatmeal boxes, noticing that some P waves arrived in the shadow zone where the liquid core model said no wave should appear, and reasoning that the only possible explanation was a solid sphere at the center, deflecting them back into the forbidden region. From faint lines on paper and the careful comparison of expected against observed, they drew the map of a world that no human being has ever seen, and no human being ever will. That is the thing to carry into sleep with you, if anything from this long night is going to settle somewhere in the quiet of your mind. Not the numbers, why? Though the numbers are astonishing, not the pressures and temperatures, not the kilometers and the gigapascals, as striking as those are. The thing to carry is the method, the way of knowing, the fact that a handful of people working in the first decades of the 20th century, equipped with instruments that were, by current standards, simple. Strips of paper, mechanical springs, the patient accumulation of handwritten records, managed to see through a planet. They could not drill through it, they could not send a probe, they could not observe the interior directly in any way, but they could listen. They could wait for earthquakes and record the waves and notice the discrepancies and reason about what kind of interior would produce exactly those discrepancies and no others. Mohorovičić, reading his seismographs in 1909 and noticing that some waves from a Balkan earthquake had arrived too quickly, as though they had taken a shortcut through faster material below the crust, and from that single observation identifying the boundary between the crust and the mantle. Gutenberg in 1913 reading the shadow zone, that ring of silence between roughly 103 and 142 degrees of angular distance from any major earthquake where the ground went quiet, where the direct S waves should have arrived and did not, where the P waves were bent and redirected. And from the shape of that silence, calculating the depth and size of the liquid core to within a few tens of kilometers of the value that a century of subsequent refinement would converge upon. Lehmann, in 1936, noticing the ghost waves in the shadow, the faint P-wave arrivals that appeared in the region of quiet, where no direct wave should have been, and reasoning through the geometry of reflection and refraction until the only model that worked was one in which there was something solid at the center of the liquid sphere. And writing it up in a paper, she titled simply, with the symbol for the wave she was discussing, P', and being right. 3 people, 3 observations, 3 moments of careful attention to the gap between what was expected and what was found, and from those 3 moments, the architecture of the deep earth. It is a different kind of exploration than the one we celebrate most easily. We have photographs of every planet in the solar system. We have samples from the Moon, and we will eventually have samples from Mars. We can point our telescopes at stars so distant that the light reaching us left them before the Earth existed. The exploration of outer space has an iconography: rockets, spacesuits, the blue marble photograph, the pale blue dot. It is exploration by going, by sending, by arriving. The exploration of the interior is not like that. It has no iconography of arrival because no one has arrived. Its exploration is entirely epistemic, but a word that means simply having to do with knowing. It is exploration by inference, by listening, by the patient construction of models that account for every measurement ever made, revised, and refined until the residuals are small enough to trust. Its heroes are people sitting at desks, reading records, noticing small discrepancies, thinking carefully about what kind of world would produce exactly those discrepancies. And the result is a map. Not a perfect map, it is still being drawn, and there are regions of it, like the great slow provinces at the base of the mantle, where the contours are known but the meaning is still under discussion. But a map that is, in its broad strokes, trustworthy in a way that would have seemed like magic to anyone who thought carefully about the problem before Mohorovičić sat down with his seismographs in 1909. The outer core is liquid. We know this because shear waves that should cross it cannot. They stop, and their stopping is the proof. The inner core is solid. We know this because faint waves arrive in the shadow where no direct wave can go, reflected off a surface that has no business being there unless something solid sits at the center of the liquid. The mantle convects slowly in cycles of hundreds of millions of years, carrying heat from the core toward the surface. We know this because the tomographic images show cold slabs descending from the surface and, in some places, warm plumes rising from the depths. The core is iron and nickel with some amount of lighter elements mixed in. We know this because pure iron-nickel is fractionally too dense to match the wave speeds. The data is too precise to be fooled by composition, and so we infer that something lighter, perhaps sulfur, perhaps oxygen, perhaps silicon, has been there since the planet formed and has never fully separated out. And at the very center, at the point where the pressure reaches 360 gigapascals and the temperature reaches something close to the surface of the Sun, there is a sphere of solid iron roughly the size of 70% of the Moon, turning slowly inside the liquid iron that surrounds it, itself turning inside the mantle, itself turning inside the thin, brittle shell of the crust on which every mountain and ocean and living thing resides. All of this inferred from the arrival times of waves on distant instruments, all of it known without being seen. There is a kind of patience in this that belongs to the deepest kind of science. Not the patience of waiting for technology to catch up, though that is part of it, but the patience of accepting that some things cannot be reached by going and must be known by listening instead. It is the patience of Inga Lehmann sorting her cards in oatmeal boxes, knowing that the answer was in there somewhere if she was careful enough, if she was systematic enough, if she was willing to take the data seriously, even when it said something strange. Strange things in data are not usually errors, they are usually messages. The faint P waves in the shadow zone were a message from the center of the Earth, and she read it. If you are still listening, somewhere in the gradual quiet of where your mind goes when sleep begins to come, this might be the image to let settle in. Not the numbers, though the numbers are real and astonishing, not the machinery of it, the seismographs and the diamond anvil cells and the tomographic models, but the image of the patient listener, the seismograph needle, waiting, the earthquake happening somewhere across the planet, in a subduction zone under the Pacific or along a fault in Central Asia, sending its waves outward through the rock and the iron and the silicate and the pressure and the dark. The waves traveling for 20 minutes through the interior of the planet, touching every boundary, reflecting off the inner core, converting from one type to another at the mantle core interface, and eventually arriving at the surface, at a quiet station in a basement somewhere, moving a needle by less than a width of a human hair. And someone, somewhere, reading it. The planet has been speaking through its earthquakes for as long as there have been earthquakes, which is to say, for as long as the plates have been moving, which is to say, for billions of years. We have only been listening carefully for a little over 100. And in that 100 years, from a standing start, with nothing but careful observation and the mathematics of wave propagation, we have drawn a detailed map of a place we can never enter, have named its boundaries for the people who found them, have estimated the conditions at its center to within a few hundred degrees and a few tens of gigapascals, have built a three-dimensional portrait of the mantle's thermal structure, and have identified 2 continent-sized provinces at the base of the mantle that we can describe precisely and have not yet fully explained. The unexplained parts are not failures, they are the frontier, the place where the next careful listener we'll find the next strange signal in the data and ask what kind of world could produce it. The map is not finished. Maps of the real world are never finished, but it is extraordinarily detailed for something drawn entirely from the outside by people who could never go in. Somewhere below you right now, below the floor, and the soil and the rock beneath the soil, the layers are descending in their slow sequence. The crust, thin as an eggshell relative to the hole. The mantle, thick and slow and not quite solid and not quite liquid in any sense that maps easily onto surface experience. The core mantle boundary, 2,890 kilometers down, the largest density contrast anywhere inside the planet, a boundary larger than the boundary between rock and air at the surface. The liquid outer core churning in the geodynamo that has been running for billions of years, generating the magnetic field that deflects the solar wind from the atmosphere that allows the compass to point north, that makes the aurora at the poles. And at the center, the solid inner core, 5,200 degrees and 360 gigapascals of pressure, solid by squeeze, silent and dark and immense, and not much larger in the scale of things than the moon. It is all there, it has always been there. And for almost all of human history, no one knew it. Not the layers, not the boundaries, not the composition, not the conditions, not any of it. The knowledge is recent, the map is new, and it was made entirely by listening to the silence. If you feel moved to leave a word in the comments about where in the world you are lying awake or drifting to sleep tonight, it would be a genuine pleasure to know. The comments are there, and they are read. There is something right about knowing that people in many different places on the surface of the same planet, with the same interior beneath them, heard this together. And if you found your way here for the first time tonight, and this kind of slow story is the kind of company you want in the dark, there are more of them here. Of the same unhurried kind, on the same strange questions that the world turns out to contain when you look carefully enough. But for now, the seismograph is quiet. The waves from the last great earthquake have traveled their paths and been recorded. The geodynamo is running in the iron below. The solid inner core is turning slowly inside the liquid that surrounds it. The mantle plumes are rising, millimeter by year, from the base of the mantle toward the surface, carrying heat that has been traveling upward for billions of years and has not yet arrived. You have followed the waves all the way down tonight, through every layer, to the center of a world no instrument has ever touched. You know its boundaries by name. You know the people who found them, and something of how they found them, and what kind of patience that work required. That is enough, more than enough. History will still be here in the morning. For now, rest.